Hello guys, so today we're doing LeetCode question 104, maximum depth of a binary tree, which is an easy question. The question is, given the root of a binary tree, return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from root node down to the farthest leaf node. So example 1, the root is 3. It has left child node of 9, right child node of 20. 20 has a left child node of 15 and a right child node of 7. So the output is 3 because the length of the tree is 3. As you go 1, 2, 3 is the maximum depth. The example 2 root is 1 with a left child node of null, right child node of 2. The output is 2 because the maximum depth is 2. So level 1 of 1 and the child node 2. So pretty much you have to get the maximum depth of the binary tree, and there's two ways of doing this. You can do it using depth first search or breadth first search. So I'm going to show you breadth first search first because I find it easier, and let me give you an example here. So again, let's say we have a tree of let's go 1, 2, 3, 4. Again, we create a queue and a count. And in a queue, we first input the root, so which will be 1. The count will be 0. Now we iterate through the queue until it is null, until it is empty. So the first thing we do is we check the children. So we know it has we get a node, the first node in the queue, by shifting it. So we get node which is equal to 1. And so since we shift it, it disappears from the queue, moves from the queue. We get the children. So if it has a left child or right child, we add it to the queue. So we know it has a left child of 2, so we add that to the queue. And we have a left child of 3, a right child of 3, we add that to the queue. And now we increment the count. We've gone through one level, count 1. Now we check those next two. We shift the first node, which is 2. We check if 2 has children. It has a left child node of, by the way, these are pushed as an array, so that will count as one level. It has a left child node of 4, so we push that here, 4. And it has no right child node. So we then go to the next number, which is 3. We shift 3 from the list. 3 has no child nodes, so complete that. We've done that level. We now we increment the count. That's now it's 2 levels. Now we go to the next queue. We shift the value, which is 4. Remove it from the queue. Queue has no child nodes, so remove it. Now queue is empty. Now so we increment the count first. Count is 3. And now queue is empty, so we break the while loop and we return the count, which is 3. As you can see, there's 3 levels: level 1, level 2, level 3. So that's the maximum depth of the tree. Let me try to do this in code. So first we create a queue, which we input root as the first value. Then we iterate through the queue while the length of it is bigger than 0. We save the length of the queue as another variable, so we can iterate through each node in the current level. So the length is equal to queue.length. Now, while the length is bigger than 0, we check the length's child node. So first we get the first node by shifting it, which also removes it from the queue. Queue.shift, sorry. Queue.shift. Then we check if it has a right node and a left node. So if node to left, we push it to the queue. If it has a right node, then we push that to the queue as well. Queue.push node.right. And then to signify we've gone through one node, we decrement the length. And we increment the count. And we would return the count as well. Return the count. Let's run. Count plus. Oh yeah, I forgot to initiate the count. Sorry, let count equal to 0. Now let's run. Let's submit. if no dot left. Okay, so it's an empty root, so create a base case. So if there is no root, then we return 0, because otherwise we input this and we iterate the while loop, but there is no root, so it will never be a no dot left or no dot right. Let's submit that. So let's run. Let me submit. As you can see, it passes on the fastest methods. Again, this is time complexity of ON, because we iterate through the tree, and time complexity of ON, worst case we store the whole tree as well. Okay, now I'm going to show you the depth first search method with recursion. So let's empty this whiteboard. Okay, I should have kept the tree. So let's say we have again tree of 1, 2, 3, 4. So the way we do this with recursion is we get the current root node, which is 1, and we return the max every time we go down a tree. We add 1. We return the max of left and right. So as we go down to 2, we know there's a left, so we return 1 plus 1, or there's no right moment, so we return 1 plus 1 or 0 plus 1. So we do 1 plus 1 is 2. So 2 plus 1, 2 is bigger than 0. And we go down to the next one. We found 1, so we can either do 1 plus 2, which is 3, or the right side, which is 0 plus 1. So 3 or 1, which is bigger? 3. So we return 3. Go back up to 2, there's no right node. Go up to 1, there is a right node, which is 3. So this will be 2. So 1 plus 1 is 2, or 3, which is the current max. So we keep 3. And we return that, which is 3. So 3 is the length of the tree. Look, 1, 2, 3. That's correct. Let me show you how to do this. So again, we keep the base case of if no root, return 0. Then we create a depth first search function. So function depth first search, pass the root. Then if there is no root, we return 0 again. And then we'll do a depth first search of root dot left, depth first search of root dot right. So we'll set this value as left, set this value as right. Then we return the max. So math.max between left plus 1 and right plus 1. If we don't increment it, it will always be 0, 0, 0, 0, 0. So each level we do, we increment plus 1, plus 1, plus 1, etc. And then we execute a function and we return it. So return DFS root. Let's submit. Well, let's run first. Let left equals, let right equals. Let's run. You see it passes. Let's submit. As you can see, it's one of the fast methods again. It has a time complexity of ON as we loop through the whole tree, worst case, and a space complexity of O1 as we're only storing the value of the depth of the tree. Thanks for watching.